Hello there, we're going to have a look at differential equations. This is our first of the video series on differential equations. These are the most interesting, fascinating little beasties you ever saw. And they're very, very relevant to life in general because there's heaps and heaps of real life situations which you can model with differential equations and solve them to find out what is going on in terms of one variable expressed in terms of another. And I'll just show you as we go. That's probably the best way. A differential equation is something which has a derivative in it, okay? So there you go. A differential equation is an equation which involves at least one derivative. And in order to solve the differential equation, you have to anti-derive, right? So there's dx dt equals cos t. That is a differential equation. It's called a first-order differential equation because it's a first derivative of x with respect to t. To solve that, you would have to anti-differentiate x with respect to t to get x as a function of t. This beastie here is a second order one because it's a second derivative, so you've actually got to anti-derive twice to solve that for x in terms of t. This one here is a first derivative of y in terms of x. That's a first order differential equation. And you know, ladies and gentlemen, from what we've been doing in anti-differentiation, that to solve that you'd actually have to do the flip technique where you have to turn it into dx dy as a function of y and then integrate with respect to x. Wait a minute, to get, what did I say? Dx dy, you have to integrate with respect to y to get x as a function of y, that's right. And then if you wanted to get y as a function of x, you'd have to rearrange the resultant antiderivative expression, okay? But enough of all that. We'll get into these and have a marvellous time doing them, and you'll see it all revealed before your wondrous beady eyes. Now, such equations are used to describe many scientific and engineering principles. That's what I was trying to say before, and their study is a major branch of mathematics, one which I particularly like. For specialist math, only a limited variety of these differential equations will be considered, but don't be disappointed, they're fascinating ones, okay? The following notation is used to describe the y value of a given x value. So this means y, when x is naught, that's the spot for the x, okay? Y, when x is naught, is 4, okay? Means, yeah, when x is naught, y is 4. Got it? Great. Now, a differential equation contains derivatives of a particular function or variable. Its solution is a clear definition of the function or relation without any derivatives included, all right? As you'll see. So, if dx dt equals cos t, then x would be the antiderivative of cos t with respect to t. Yeah, that would be sine t plus the constant of integration with which we are now very familiar. Okay, that's the general solution because it has the little the c thingy in there. Yeah, where that could allow for any constant which might be there. In order to get particular solutions, further information is required, usually given as an ordered pair belonging to the function or relation. I call it an initial condition or a boundary condition, which gives us one coordinate point on the anti-derived or original function, okay? But for equations with second derivatives, you need two of these boundary conditions in order to work it out. Once you substitute the values of those boundary conditions in, you can work out what the constants of integration actually are, and there's no generality involved in all. You've got a specific solution. All right, let's do some. So we've got to verify in this case that y is a e to the x minus 1 is a solution of the differential equation dy dx equals x plus y. Well, goodness gracious me. And then we've got to find the particular solution of the differential equation. This is a boundary condition. Look, don't look now. That's a boundary condition or initial condition which says that when x is naught, y is 3. So we're going to substitute that in to solve for the value of our constant of integration. Now, look, guys, it's not actually asking you to solve the DE at all. It's just it's actually giving you the solution and asking you to prove that it's the solution of this. So what you do is you have to plug this expression into here, that expression there for y, to see whether it works in this differential equation. So you'd have to do the derivative, then put that as dy dx as the left-hand side of your equation, and then for the right-hand side you'd have to put y plus x in terms of x, as the solution is in terms of x, and see whether the left-hand side and the right-hand side match up under and are equal. If they are equal, yes, you have verified that that is a solution. Okay? That's as simple as that. That's all you do to verify. Some students get very confused with that, so don't be confused. It's easy. So here we go. If y equals that thing, then I'm going to do the derivative of it. dy dx equals now. Do you agree with that? A e to the x minus 1 for the x term, the derivative of. There's no derivative of this term here. The derivative of that is 0. So there's our derivative, right? So now what we're going to do is we're going to substitute this into our differential equation and see if the left-hand side equals the right-hand side, which I can assure you it will, because I've already done it. Left-hand side is dy dx, which is that thing. Yeah, we just worked it out up there, didn't we? Right, now what about the right-hand side? The right-hand side is x plus y, and y is already this beastie, all right? So here it comes. There it is, x plus, all of this is the y, and look, mercifully these x terms cancel out, and what do we get? We get exactly the left-hand side. Isn't it beautiful? So therefore, we can say the left-hand side equals the right-hand side, and therefore y equals a e to the x minus 1 is a solution as required. You might like to put something fancy like Latin, QED, capital Q, capital E, capital D, instead of as required in brackets, or you might like to put proven with a couple of exclamation marks there. You might like to do that as well, you know. That as long as you're saying that this is the point where I believe I have shown what you asked me to show, then that's fine. Okay. I think QED stands for quid est dem or something. I don't know, something like that, which means which is the thing. That's what it means anyway. Now B for you and me. Now, okay, so we're saying that. What are we going to show here? Hence find the particular solution of the differential equation. Yeah, okay. Well, we know that y equals ae to the x minus 1. Now, this a is a beastie that we've got to sort out here, because that's just a constant. And if we can substitute the value of whatever they just told us, what was it? When x is 0, y is 3, well, we can then work out, put the x value here and the y value there, and then a will be all that's left that's unknown, and we can work it out. Okay, here we go. There it is, yes, see? And that's very nice, isn't it? E to the 0 is 1, so that's 3 equals a minus 1, and therefore a would be 4. Terrific, isn't it? So therefore, look, we've sorted it out. We've got the specific solution, and y is 4 e to the x minus 1. Do you like it? It's beautiful, isn't it? Okay, so next one, verify again. This is another verify one, so it's all the left-hand side equals the right-hand side stuff again, right? Y equals e to the 2x apparently is the solution of that differential equation. So the differential equation is a second order DE. We've got to take the second derivative of y equals e to the 2x, the first derivative of y equals e to the 2x, substitute them into this equation as the left-hand side with that term, and that term, and hopefully they'll come out to be 0, which is the right-hand term, and if they the right-hand side. And if they do, we've proved it. Okay, so if y equals e to the 2x, therefore dy dx would be 2e to the 2x, and d2y dx squared is how you say that second derivative thingy, d2y dx squared, that'll be 4e to the 2x. Now it's time to plug and play, guys. We substitute the equation to check whether the left-hand side equals the right-hand side, and left-hand side now. Left-hand side equals, right, that's the d2y dx squared, that's the dy dx, and that's minus 6 times y, because they told us y was e to the 2x, and is that going to come out to be, oh yes it is, to be 0, lovely. It comes out to be 0, and that's equal to the right hand side, so we've just proved it. We've just proved that e to the 2x as our value for y is the solution, is a solution anyway, of that differential equation. Yes, yes, very good, thank you Mr. Box. How are you going? Are you getting this? Are you happy? Very good, I'm glad you are. Now here's another one, another verify, okay? This is rather marvellous, we're getting good at this now. So y equals, what does it equal now? A e to the 2x plus b e to the minus 3x, okay. We have to show that that is a solution to this DE. Well, I don't need to tell you what to do anymore. Of course you know what to do. You take the first derivative, then the second derivative, so that gets you that term to plug in. Yeah, the first derivative term goes there, minus 6y goes there if y is that. The whole thing's got to be in terms of x, right? and hopefully that'll all come out to be 0, which is the right-hand side, in which case we've proved it again. Right, so why is that? Here comes dy dx. Now, see if you agree. See if you agree. Yeah, I think that's right. Yes. Now, here comes the second derivative now. Have a good look. Cast your eye upon it. Yes, I like it, don't you? Now let's plug and play now into our left-hand side. There's the, oh goodness, there's our left-hand side. So it's there's the d2y dx squared, those two terms. There's, what's that? That's dy dx, and there's minus 6y, right? Goodness, look, it's a lot of stuff, isn't it? Now, does that come out to be 0? We've got a's and b's here, so we've got to be careful. There's 4a e to the 2x there. Another 2, which gets us 6. Oh, look, and minus 6 of them. Beautiful! And now what about the b's? Plus 9b e to the minus 3x. There's minus 3 of them and minus 6 of them. Ah, truly marvellous. That comes out to be 0. So therefore that equals the right-hand side, and therefore we have shown it. We've shown it that that is a solution of the DE. All right, you're okay? Good. Thank you, Mr. Box. Now what's up? What's up next? Oh. All right, find the constants A and B if this is a solution of the DE. Oh, that's pretty interesting, isn't it? All right, that's all right. So the whole thing's got this has got an A and a B in it. So we've got to actually say, well, we know this is the solution, and if it is the solution, what would the values of A and B be? Pardon me getting mixed up with all the B's. Come on, it's easy. You know what to do. You know what to do. Right. Why is that? I think I'm going to multiply those brackets out so I don't get confused. So we've got to do dy dx and we've got to do dy dx squared. Okay, come on. Fasten your seatbelts. Here we go. Oh, heavens, what's that? Dy dx equals 2 times, I see, because this is a product rule thing. It's a product rule. So it's left d right plus right d left, as I say. There's left d right plus right g left is the derivative of x with respect to x is 1, plus the derivative of this, which is 4 e to the 4x. That's all right. I think we better multiply all that out and collect our ducklings. Yeah, our like terms, e.g. our like terms. So what's that? It's 8x e to the 4x plus 2 e to the 4x, that's right, plus another 4. So these two are going to combine, right? That gets us that. Now that's a bit easier, isn't it? Now I think we can launch into our second derivative now. Good heavens. Be careful. 8 times, okay, left d right plus right d left plus 24 of them now. Good heavens. I think we better simplify that now. Getting rid of that bracket. That looks right, doesn't it? Or doesn't it? Yes, it does. Yes. Are you agreeing? Yes, and these ones can be combined, so 24 and 8 are 32, so it looks like it's 32x e to the 4x plus 32 e to the 4x, yes? Okay, alright. Thank goodness for that. Now, we're going to plug it into here. That's the second derivative there. The a times the first derivative, that's the first derivative, plus b times y, where y is that. And that we've got to make that equal to 0, and hence, solve it for a and b such that it is equal to 0, right? A little bit different from the straight verify ones. Now, sub into the DES to find a and b. Now, left-hand side is equal to that thingy, isn't it, right? That's straight from up here. Now, substituting our values in, be very careful. Look, there's e to the x's everywhere here. It's like a forest of them. So there's our d2y dx squared. There's minus a times dy dx, is that right? Where's dy dx? Yes, that looks alright. Plus b times this thingy, alright? Now I know, no, don't panic, it's alright. We're gonna get rid of those brackets and collect our like terms, guys. Now, that's rid of the brackets. Now, we've got x e to the 4x terms, and we've just got e to the 4x terms. So there's an x e to the 4x, there's another x e to the 4x, and there's another x e to the 4x. This one's just a e to the 4x, and this one's just an e to the 4x. So we'll collect them, suitably agglomerate them together. There's our x e to the 4x. So there was 32 minus 8a plus 2b, yes, I get that, plus e to the 4x. Now that was one of them. Where's the other one? This one's another one, and that one's another one. And now make sure you write your B's properly and don't let them morph into 6s, guys. Make sure they've got a nice straight back on them and no curvature of the spine. Otherwise they could turn into 6s and you'll get the wrong answer. Now, we have to say this plus this equals naught. Okay, now what does that all mean? Good gracious. Okay, look, it has to mean, basically, we can't have e to the 4x equal to naught because that never equals naught. It approaches naught, but it never equals naught. So therefore, what we are saying is, this, what am I saying? Wait a minute. Oh yeah, this one, minus 8a plus 2b plus 32 has to equal naught, presuming x itself isn't equal to naught. Oh, but even if x was equal to naught, guys, see, this has also got to equal to naught, right? This has got to equal naught. So we're assuming that x itself is not equal to naught. Yes, we are. So therefore we can say this term, this coefficient has to be naught, and this coefficient here has to be naught. And I think we can solve that simultaneously quite easily, can't we? Yes, there it goes. Look, simultaneous equations. So we can divide through. Well, we certainly can in equation 1. So we've got, yes, that's minus 4a plus 1b is minus 16, taking that 32 over the other side and dividing by 2. And that's the other one. Yeah, that one's the other one. Rearranged a bit. Now, what are we going to do to solve this, guys? Well, I think we'd probably do it by elimination, getting rid of these b's, won't we? Yes, subtract 2a from 1a, which would get us minus 4a plus 6a, because it's minus a minus, yes. B's are all gone, goodbye, equals minus 16 plus 32, which is going to be, yes, that's very good. So it looks like a is 8. A is 8. A is 8, and it's great. Now we can substitute back for a into one of those equations somewhere. I'll put it into 1a, which is this one. So if a is 8, it's going to be minus 32 plus b equals minus 16. And therefore, yes, and therefore b will be 16. There it is. There it is, guys. There's your answer. So a is 8 and b is 16. Okay, there it's good. Now, I'm just thinking. No, that's all right. I was just thinking about this this thing up here when I was doing these coefficients had to equal 0. I was thinking about this x, but it wouldn't work if just x was 0, because then this wouldn't be 0 anyway. I'm just trying to work out whether I was completely right with my logic. Yeah, so it's safe to assume this is 0 and this is 0. Yeah, don't worry about it. I'm just ranting and raving here. Do you get the idea? You do, don't you? Yes, all right. So that's the end, and the end is your friend. But only if you go and do plenty of practice, okay? But this is just the start of the exciting journey into differential equations. They are beautiful things. You wait till we do Newton's law of cooling and Torricelli's law and all kinds of marvellous things. Just you wait. You'll be really surprised and delighted by differential equations. So I'll see you next time. All the best and have a great day.